So we will continue our discussion with equivalence of regular expression and finite automata. So in the previous lecture, we already seen what is regular expression and how to design regular expression. So basically, you know that regular expression, it can accept some set of strings. So that string which regular expression will accept, that will be over the input alphabet. And these strings, the set of string, it is also called as a regular set, or it is also called as a language. So as you all know, the language is nothing but a set of strings, and those strings will be those strings will use the symbols from the input alphabet. And the regular expression also denotes the set of strings uh, over a particular input alphabet, and that set of string is nothing but the language. The way your finite automata accepts the language, similarly your regular expression also accepts the set of strings or the language. Now, for every regular expression, there exists a finite automata. So once you have a regular expression, that regular expression you can convert to the finite automata, and that finite automata or regular expression will accept some language, and which is denoted by your regular expression. So finite automata accepts language. Finite automata can be expressed with regular expression, or you can say regular expression can be converted to finite automata. So, and both will accept the same language. So this is known as the Kleen's theorem. So this Kleen's theorem, it has got two steps, or it is showing two things, that any regular language, it is accepted by the finite automata, and languages accepted by finite automata are regular. This is what is the meaning of your Kleen's theorem, that every language, regular language, is accepted by finite automata, and languages which are accepted by finite automata are regular. Okay. So now if you want to convert any regular expression to finite automata, then you will have to follow these three steps. First, you have to obtain the NFA with epsilon transitions. That is, from regular expression, given the regular expression, you have to obtain the non-deterministic finite automata that will have epsilon transitions. Then convert that NFA with epsilon transition to NFA without epsilon transition, and then convert that NFA to DFA. So the last two steps, you know how to convert NFA with epsilon transition to NFA without epsilon transition, and then convert NFA to DFA. So these last two steps, you know. Now we will talk about the first step, that how to convert your regular expression to NFA with epsilon transition. So kindly take a note of this. So if you have 0 plus 1, if this is your regular expression, so this you can denote in the form of NFA like this. So two parallel paths. So if you are starting from this particular state, then from here there is one path for 0, and from here same state you have another path for 1. So this way the two parallel path 0 or 1, this you can denote. Now if you have a concatenation like this, so you can convert this regular expression in the finite automata like this. So initially you will have a transition for a 0 from one state to another state, then there is a epsilon move, and then you have a transition on 1. If you have a closure, then that closure, that is occurrence of 0 for 0 or more number of times. So if you'll consider this, so this way this closure can be shown, where you can show the occurrence of 0 multiple times. So this is how you can move. So here it is, occurrence of 0 multiple times. and there will be one more state here and one more state here, and you can show this bypass arrow like this. So you will have the uh, occurrence of zero number of times. So this way you can convert your regular expression to NFA. I want you all to take a note of this. I'll give you 5 minutes time. Meantime, you just uh, copy these things. So if you have a regular expression, say R is equal to A dot, say A plus B, plus B star. So if we want to convert this regular expression to NFA, so how we will start? So initially we will try to draw the parallel path. We'll try to show the parallel path for A plus B. So with me, you also try to draw, and then you can compare. So here I will have, this is for A to B. Sorry, for A. For A, am having this. Then I'll draw one more, and here I'll show it for B. So these parallel parts I'm showing. First, it is for A. First, it is for A. Second one will be for B. Now these are the parallel paths, so we need to show the common starting point for that, from where your parallel path will start, and here these parallel paths will end. So, so as we were having we have shown the parallel path for 0 plus 1. Here it is similarly, it is for A plus B. So this part we have done. And now it is star is mentioned. So it means the occurrence of A plus B, it is 0 or more number of times. So if it is multiple times, so that repetition you can show with this arrow. It is same as what you have shown the closure for 0. So consider this as your 0. So here it is repeating that this A plus B entire thing you consider as a 0 and 0 closure. So if this is your 0, then repetition of 0 will be shown with this, and 0 occurrences of 0 that you can show by drawing the bypass. And these are all your epsilon moves. And if there is 0 occurrence of A plus B, then this entire A plus B you are bypassing. So it will directly move to this, and your entire A plus B, it is bypassed. So with this you can show it is 0 occurrence of A plus B. But here we have the is a plus b. Before that we have a, single a. So that we need to show. No, set state here, it is a transition for a, and that a, it is concatenated with a plus b star. So this concatenation is with epsilon. So I'm drawing this. If here you have any doubt, you can ask me now itself. And all epsilon moves. Temporarily, I'm using this symbol for epsilon. It's like if we have a correct symbol for it. So is that clear to all? Any doubt here? Have you understood this? Am I audible? Am I
Yes,
audible?
ma'am.
So you got this, how to convert this.
Yes, ma'am.
So now here we'll have Okay, so first regular expression you take. A star plus B star. Then second regular expression, all these questions will be there in your exam. You'll get a regular expression and you'll need to draw the NFA for the same. 1.00 star dot 1 plus 0.1 0.1 dot 0 dot. Then third regular expression is 0 star plus 1 star plus two more should be there. One. So regular expression is equal to AB slash JA star dot AA dot AB slash BA star. Okay, I guess this much will be enough for your practice. So please take a note of this and solve it and submit it. Okay, done? Have you noted?
Yes, ma'am.
Okay. Now you have to solve this. You all have to answer this question. Using regular expression, represent language defined over input symbol 0, 1, 2 such that every string from the language contains any number of zeros followed by any number of ones followed by any number of twos. So first of all, you should tell the language किस type की strings आपको यहाँ पे मिलेंगी and then you try to convert it to the regular expression. So these seven problems are there in front of your screen and you should answer and you have to answer it now. You have to answer now all the seven questions. How much time you need to solve this? You can use the symbol dot asterisk and plus. At least you answer first two so that first three. At least you try to answer first three, so I'll come to know that you are on correct track. You're able to design it, and rest you can do as a homework. फर्स्ट का आंसर किसी के पास है क्या?
Yes, ma'am.
हाँ, क्या आएगा आंसर?
Yes,
0
ma'am.
star dot 1 star dot 2 star.
करेक्ट. सेकंड का? That contains at least one zero is followed by at least one one followed by at least one two. पहला जो लिखा है उसी के जैसा है, उसमें थोड़ा चेंज आपको करना पड़ेगा. Are you able to answer this second question or you want my help here? Hello, you want me to tell the answer of second question? Am I audible? Hello, am I audible?
Yes, ma'am.
सेकंड का आंसर आ रहा है कि यू वांट मी टू हेल्प? Say something, yes or no. Someone should answer no. Okay, see, what have you written there? First जो आपका problem है, there what solution you have given? 0 star dot 1 star dot 2 star. So here what is happening? You are having 0 or more occurrences of 0 followed by 0 or more occurrences of 1 followed by 0 or more occurrences of 2. Now in the second problem what they are saying, you should have at least 1 0 followed by at least 1 1. At least 1 0, there must be at least 1 0. Thereafter you can have either 0 or more occurrences of 0. So if I'll write it like this, so what I'll get here, I will have at least 1 0, and after that I will have any occurrences of 0. Similarly, I will be adding it like this. So will be having at least one, and then I will have the any number of occurrences of one. And similarly here I will be having for two. So 0, then 0 star, and this is concatenated by 1 star. So I will have at least 1 0 followed by at least 1 and then I have 2 star. So after this concatenation is of at least 1 2 and then any occurrences. So this same thing I can represent it like, you can use plus to show one or more occurrences of anything. That is, this star, if I say it represents do while, so plus, it represents while. So I can write it 0 plus dot, this plus should be the superscript, then 1 plus, then dot 2 plus. Is that clear to all?
Yes, ma'am.
Okay. Then the answer of third question, design regular expression for language that contains all strings starting and ending with A. It should start with A, it should end with A, and with any number of B's in between. It's very easy. Can anyone tell? It starts with A, ends with A. And in between, you can have any number of B's. Any, if you'll say any, it means it can be 0 or more number of B's.
Ma'am, it will be A dot B star dot A.
Correct. And if I'll say it should start with A, end with A, and there should be in between, there should be at least one B.
Then ma'am, A dot B plus dot A.
Correct. So I guess rest you can do. So when I'll share the presentation, you will find the answers of all the 7 here on the next slide. Then this is whatever answers you will get here, no, for all regular expression, you should try to draw the NFA. For all these 7, you should draw NFA. And now the last topic here, it is Arden's theorem. So Arden's theorem, it is very easy, and its proof is also very easy to understand. So if it here it is said P, Q, and R are the regular expressions, and here it is shown that if R is equal to P plus RQ or R is equal to QR plus P, then R can be simplified as PQ star. Our second, it is saying that if R is equal to P plus QR or R is equal to QR plus P, then R can be simplified as R is equal to Q star P. And this we have to prove. So considering the first case, let us consider R is equal to P plus RQ. So you can simplify it. This R can again be replaced by P plus RQ. So if you'll see this R is replaced with P plus RQ. So this P, it is as it is, this R, it is just your mathematics. And then once you will solve this bracket, you will get this P plus PQ plus RQ. Now again this R you can replace with P plus RQ. So you got this P plus RQ, and then when you will simplify it, you will get it like this. Now again this R you can replace it with P plus RQ, and then you will get it something like this. And here it goes P plus PQ plus PQ square plus R cube, and when you replace that R here, and when you will simplify it, you will get P plus PQ plus PQ square plus PQ cube plus PQ raised to 4 plus likewise. So this you can see here. And when you take P common, you'll get it like this. So star, it means 0 or more occurrences of Q. Likewise. Now, and in similar fashion, you can prove this also. Now, second case, they have said R is equal to P plus QR. And now again, you will replace this R with P plus QR. So, and solving it, finally, you will be getting this. Just go through it. I guess you all know how to solve the bracket, and this is your Arden's theorem. Is that clear to all?
Yes, ma'am.
Okay. So we will move to next topic then. Okay, now we are discussing regular language. So what is regular language? It is language, as you know, it is nothing but a set of strings over input alphabet. So what is regular language? So regular language is nothing but a set of strings accepted by the finite automata. And this regular language can be represented using regular expression. So that we have seen. So earlier part of this lecture where we have designed the regular expression, you know what type of language that regular expression will derive. So regular language, it can be represented with the finite automata and with the regular expression also. So regular sets or regular language. Regular sets are again nothing but your collection of strings over input alphabet. So regular sets or languages are closed under the same operations that are used to construct regular expressions such as plus, dot, and star. So close under the expressions, uh, uh, close under the operations, it means when you will perform any of these operations, that is this plus, dot, or star on the regular expression, whatever you will get will also be your regular language, right? So this is what is the meaning of this close under the same operation. I mean, if you have a regular expressions, and on those regular expressions, if you are performing these operations, then whatever you will get, that will be your regular set or regular language. So these are the closure properties for regular language, and theorem 1 here it is saying that if we have L1 and L2 as a regular languages, then their union is also regular languages. This is what is the meaning here. Sorry. Regular language over input alphabet is defined as every finite set of words. That means language. That finite set of words is nothing but over input alphabet is nothing but the set of strings. Again and again I'm telling. So those set of strings, you can call it as a regular set or a language. So if U and V are regular sets over input alphabet, then their union, their concatenations are also regular sets. So here U and V, it means here you are representing the language U and V, because they are the regular sets. Regular sets is nothing but the collection of words or collection of strings over input alphabet. So if you'll perform this union concatenation operation, whatever you'll get, that is also your regular set. So if S is your regular set over input alphabet, then S star we can call it as a closure of S. And it means the class of regular sets over input alphabet is the smallest class containing all finite sets of words over input alphabet and close under union concatenation and closure operation. So here we will see what are those closure properties. So if L1 and L2 are the regular languages, then their union is also regular language. So here they have shown L1 and L2 are the languages, So, and these two languages are represented by R1 and R2, these two regular expressions respectively. So, L1 will be equal to language of R1 and L2 is equal to language of R2. So, if you could perform this operation plus operation on these two regular expressions, then the language with this R1 plus R2 will represent, that is also regular language. And so we can say the language represented by R1 plus R2 is equal to language of R1 union language of R2. Similarly, you can prove for for concatenation operation also. So L1 is the language represented by R1 regular expression, L2 is the language represented by R2 regular expression. And you know that if R1 is regular expression, R2 is regular expression, their concatenation R1 dot R2 is also regular expression, and their language which R1 and R1 dot R2 will generate, that is also regular language. And that is the reason it can be denoted like this. Language of R1 dot R2 is equal to nothing but language of R1 dot language of R2. Then this is the closure. So this is Kleen's closure. So if R is a regular expression and L is a regular language, then we can say L is equal to language of R. And as we have seen earlier, R star is also a regular expression. So language of R star is also regular language, and that you can denote it like this. So here you can say the occurrence of a zero or more number of times this R will occur. So your Kleen's closure. And after that, the most important thing, it is a decision property. So decision property is nothing but it tells whether your problem is decidable or non-decidable. So to solve any problem, if there exists an algorithm, then we call it as a decidable problem. Otherwise, they are non-decidable problem. So there are four types of decision properties or decidable problems. That is emptiness, finiteness, equivalence, and the membership. So emptiness problem is whether your finite automata accepts empty language or not. So this you have to identify. So how you will identify? So for that you have algorithm. So whatever finite automata you have, from that you should eliminate inaccessible states. Inaccessible, it means where you cannot reach. There is no incoming edge to that particular state. So if there is no incoming edge to that state, it means you can't reach to those states. So you have to eliminate those inaccessible states. After eliminating that, if there exists a final state, if it is exist a final state, it means it is accepting some input. If there is no final state, it means it is not accepting anything. So if it is not accepting anything, it means it is accepting empty language. So this is the example for this. So here this Y is not reachable, it is inaccessible. So it is removed. So what you got is this. And here you don't have the final state. It means it is accepting empty language. Now here also the Z is inaccessible. So it is removed. And what you got is this. So with this finite automata, it contains final state. It means it is accepting something. And that is the reason it is non-empty language. So likewise, you can describe this emptiness problem, and there is algorithm. So that's why we call this emptiness as a decidable problem. Then finiteness problem. So here it will check whether your finite automata accepts finite number of strings, or the language which any finite automata is accepting is a finite language or not. So when your finite automata has loop, so that means it accepts infinite language. If there is no loop, it means there is finite language. So here also you have to remove inaccessible states, eliminate states from where final state is not reachable. Final state If it is the final state is not reachable from any of the states, those states also you should remove. And if the resultant finite automata, if it contains any loop, so it accepts infinite language, otherwise it is not. So this, from this two example, you can see here, this is a loop. So here you can have any number of BA, 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 BA like this. Here also you have a loop. So any number of B's, here also you have any number of A's. So likewise, because it contains loop, it accepts infinite language. There is no loop. So in this case, it is accepting finite language. Now equivalence problem. So equivalence problem is when we know that two automatas are equivalent if they accept the same language. So how you will decide whether two automatas are equivalent or not? So for that, you have to make one comparison table. So, and in that comparison table, you have to mention the final and non-final states of automatas, which you want to check whether they are equivalent or not. So, figure A, from here you identify the final state of figure A. So, A is the final state. From figure B, you identify the final state. So, figure B's final states are C and D. From figure A, you identify the non-final state. So, you have B. From figure B, you identify non-final state, it is E. Okay. Once it is done, now make a pair of final and non-final states. So if you make a final state, so it is AC and AD. You will get this pair, and non-final it is BE. So accordingly, you will be getting this pairs AC, AD, and BE. Now to this, you give both the input 0 and 1. So when you will give input 0 to state A and input 0 to state C. So input 0 to state A, you are transiting to the same state. So that is the reason here it is A. To C, you give input 0, you are transiting to D. So that is the reason here it is D. Now to A, give input 1, you are traveling to B. So that is the reason here it is B. To C, you give one input, you are moving to E. Likewise, you gave 0 and 1 input to remaining two pairs. And this is what is the output you will get here. Now, if you'll observe here in the second column, whatever you are getting, this AD, AD, AC. So AD, AD and AC. So these are all from this final state, A, D and C, or A, C and D. So this second column, it contains only final states. Whereas in first column, if you'll observe, it contains only non-final state. And because this third column contains only non-final state, this second column contains only final state, we will say that these two finite automatas are equivalent. So this is another way to identify whether they are equivalent or not. If after giving the input, if final and non-final states are separated, then we can say that they are equivalent. So here final states of both the automatas are separated than non-final states of both the automata. If you got such type of answer, it means they are equivalent. Now next problem is the membership problem. So membership problem is it gets applied on a particular string. Whether particular string is a member of the language which finite automata accepts. So how you will check when that particular string is given as an input to finite automata, and after processing that entire string, if you resides on a final state of finite automata, it means that string is a member of the language which that finite automata accepts. Otherwise, it is not. So if you have these two finite automatas over input alphabet 0, 1. So try to give multiple inputs. You will understand. You can identify whether the string is accepted by the finite automata or not. So if here it is 1, 0, it is accepted. 0, 0, it is accepted. So this is the only language this first automata is accepting, right? Now here, if in this case you will say this is the language which this finite automata is accepting. So you just have to give multiple strings that consist of 0 and 1 and check after processing that string you reach to the final state or not. So this is also a decidable problem. And next, an important topic is the pumping lemma. So pumping lemma here, it is very important theorem for regular languages. So what it is saying is that if you have some particular format of strings where some particular part is repeated, then whether that string is acceptable by finite automata or not. Or you can say here it is simply signifies the fact that if a regular language is infinite, then it must contain string of a particular form. Okay. So now if here you will observe the first string which it is accepting is A, B, B, A. And here the occurrence of A is at state 3, put C. The occurrence of A is 0 or more number of times. So if it is occurring 0 times, so it is A, B, B, A. If it is occurring once, so it is A, B, A, B, A. If it is occurring twice, so it is A, B, A, A, B, A. Twice, then it is A, B, A, 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 B, A. Likewise. So you will get infinite number of strings here. Now, you all know the graph theory. Now assume that if we have this string A, B, B, A. So for this string to travel, we need at least we need 5 nodes, right? So because for this path of A, B, B, A, if number of symbols in this are 4, then we need 5 states or 5 nodes to travel. So if we have 4, we need 5 states. If we have 4 number of symbols in the string, then we need 5 nodes for its traversal. So it means if we have n number of symbols in the string, we'll need n plus 1 nodes. But now if you take the example of this, here if the repetition of A is more, if you take this string, if you take this string here, and 1, 2, 3, 4, 5, 6, 7, 8. 8 symbols are there in this string. So if 8 symbols are there, it means we should have 9 nodes to traverse these strings, but we have only, let's say, 5 nodes or 5 states. So it is not feasible that for 8 symbols we don't have 9 different or distinct states. So if that is not possible here in this case, it means there must be some state where which is repeated, or where there is a loop, or on that particular state the input symbol is pumped. And this is what, and though it is so, still that particular string is accepted by the finite automata. This is what is the meaning of pumping lemma for regular languages in a simplest and layman's language. So if you see, this is the proof of it. So you can go through it, and I hope you will understand, because this language is also easy. This you just have to go through it, and whatever I've explained just now, if you could remember this, and if you could relate that explanation with this content, you will understand what is pumping lemma for regular languages.